Hi, everyone. The topic of this video is mixtures. We're going to start talking about how matter can mix together into various solutions. When we talk about the classification of matter, which we didn't really discuss much when we first began talking about matter in this course, but matter can be loosely grouped into two different classifications according to its makeup and how pure it is. We've spent a fair bit of time already talking about this side of the chart, where we can have a pure substance, which could be either an element, something like pure gold, pure silver, pure oxygen, and so forth, and how elements can be either monatomic or diatomic. We talked about O2, N2, F2, and so forth. We can also have compounds that are pure substances, and we discussed either ionic or covalent with those. You know, a metal and a non-metal coming together, NaCl, sodium chloride, in order to form an ionic compound, or two non-metals coming together, maybe hydrogen and water hydrogen and oxygen to make water, or carbon and oxygen making carbon monoxide, carbon dioxide, things like that for a covalent substance. And so we've discussed some of this already. Matter can also be a mixture, though, made up of one or more types of elements or compounds mixed together. And that's where we're going to spend a little bit more of our time today. And so this just sort of breaks it down a little bit more. And so again, we've seen some of this already, but we have pure substances that are elemental, consisting of just a single element. A compound consists of more than one element, but the key here, in order for it to be still considered a pure substance, is that a compound can be depicted by a chemical formula. And in the case of a pure substance, or in the case of a compound, that means you're only going to have one compound there with one chemical formula. If you begin to have more, if you have maybe some H2O and some C6H12O6, a little bit of glucose in there, now you have two compounds, two chemical formulas. That's going to be a mixture. And we'll talk about the different types of mixtures, homogeneous and heterogeneous, in just a minute. So like we've already mentioned, over here on the pure substances side, elemental, one type of atom, compound, two or more, chemical formulas. Mixtures can either be homogeneous or heterogeneous, homogeneous or heterogeneous, however you want to pronounce those. In a homogeneous mixture, also called a solution, the composition is completely uniform throughout, and we'll look at some examples of that. In a heterogeneous mixture, the composition is not uniform. And so we can see some examples of that here already. And so we're starting to get into some warm weather. And so you might be mixing up some iced tea, something like that, or mixing up some lemonade. Something like that would be a homogeneous mixture. Again, maybe, assuming that it was dilute enough so you didn't still have the solid settled at the bottom. But that would be a homogeneous mixture because it's all completely the same throughout. Your first sip of tea is going to be pretty much identical to your last sip of tea. And you can even see the mixture as you look through it. It's all nice and evenly spread. As opposed to a heterogeneous mixture, so picture something like granite. There are easily seen visual differences in parts of it. And so the composition is not the same throughout the whole thing. And that's really seen here when we look at some of the differences. And so here we have a glass of just pure water. So that's a pure substance. That would be a compound, H2O. Now we've made some lemonade from a powdered mix. And we can see here that it's all completely uniform throughout the whole thing. So that's a homogeneous mixture. Make some delicious lemonade from fresh squeezed melons. Oh, whoa, what's going on there? There we go. And now we've got all that pulp floating around in there. And so there are definite differences in the composition in different parts of the whole mixture. So that is now a heterogeneous mixture. And so just some more of the terminology surrounding mixtures. So it's anytime, like we mentioned, that we have a combination of two or more elements and or compounds in any sort of proportion is going to be a mixture. Typically, mixtures can be separated into their components by using some sort of physical separation technique. And so keep it like the example of the pulp in the iced tea. We could filter that out and we would be able to separate the two mixture components. If you had a mixture of, for instance, crude gas or crude oil is absolutely a mixture when it comes up through the, sorry, when it comes, when we actually get it up through the earth. But then we can start to use distillation techniques to actually separate out the individual compounds. Talked about the two basic mixture types, heterogeneous and homogeneous. Components of a homogeneous mixture are evenly distributed. Components of a heterogeneous mixture are unevenly distributed. We also have mixtures that we call colloidal dispersions. So some of the differences here are, or what really, I guess the big difference is that with a colloidal dispersion, it's probably going to look fairly cloudy. In colloidal dispersions, first of all, the major component, which you have the most of, is called the medium. The minor component, and so you can think of this as what's being dissolved, although it's not really dissolving in there. The minor components are called the colloids. A colloidal solution is any solution that has particles which range in size between 1 and 1,000 nanometers in diameter, but they're evenly distributed throughout the solution. And and this is the key, they remain dispersed and they don't settle to the bottom. And so they're not big enough that the particles are going to eventually settle to the bottom of the glass or whatever you might have it in. The particles remain dispersed throughout the whole thing. They always remain dispersed. And that's the key aspect of a colloidal dispersion. A few different examples. Colloids typically are opaque, and we do find them in all three different states of matter. Aerosols are solids or liquid colloids in a gas medium, so something like fog could actually be considered to be, or smog even, would be considered to be a colloid. We have what we call sols, which are solids dispersed in a liquid medium. That's what paint essentially is. Emulsions, liquid colloids in another liquid medium, mayonnaise. Or gels, liquid colloids in a solid medium. That's what gelatin is. Another type of mixtures are suspensions. Suspensions start to have larger particles in there than what a colloidal mixture does. In a suspension, the particles are larger than 1 micrometer. They will eventually settle. And so if you leave a suspension alone long enough, the particles are eventually going to settle to the bottom of the container. Some medications are prepared as suspensions for people who have difficulty with pills. And so it's important if a medication is in a suspension form that it has to be very well mixed. Because you want to make sure that if it has settled, you want to make sure that you're getting the actual drug that you need up into the mixture so that it is taken in. Sometimes suspensions have to be separated, and that's what a centrifuge is for. You may have seen centrifuges, especially they love to show centrifuges on shows like, or any show that's trying to show you science. They'll throw something into a centrifuge and have it spin around for a while, and then that's very sciencey for anyone watching. But what a centrifuge does is it will spin at very high speeds and force those particles in a suspension. It will force them down into the bottom, and that's that we call the pellet. And that portion that does not settle is called the supernatant. The type of solution that we're, or the type of mixture rather, that we are most likely going to be working with in this course is a solution. Solutions are homogeneous mixtures that consist of small molecules, atoms, or ions with diameters less than a nanometer. And so very, very small particles in there that end up evenly distributed throughout the whole solution. And they don't settle out, they stay distributed in there. The component that's present in the greatest amount is called the solvent. It's probably a term you've heard before. Component in the lesser amount is the solute. Now, for most of our purposes, yes, water is usually going to be our solvent. But don't fall for that trap of thinking that water is always going to be the solvent, because the technical definition is that the component that is in the greatest amount is the solvent. And so a good example of this would be something like 95% ethanol. So 95% ethanol is something that is used in laboratory settings quite often for various purposes, quite often as a solvent, actually. But that 95% ethanol means that 95% is the actual chemical compound ethanol. Ethanol, which would have a chemical formula of so CH3, CH2OH. By the way, we'll see in later in later lectures when we get to organic chemistry topics why I am not writing this as C5H6O. Be the same thing either way. But there's a reason that we write these out like this quite often, and we'll see that when we get to organic chemistry later in the course. But anyway, 95% ethanol means that we have that 95% of the substance in there is our ethanol. Only 5% is water. So in that case, absolutely, ethanol is our solvent, and water, no idea why I wrote a W there, because the word solute certainly doesn't contain a W, but water is our solute. And so that's why I say don't always fall for that trap of thinking that water is going to be the solvent. In most solutions that we use, it will be, but keep in mind the actual technical definitions there. Solutions where water is the solvent are known as aqueous solutions, and they're abbreviated as AQ. And so that's important to note, because if you see something like this, perhaps, so NaCl, AQ, this means that what we actually have is NaCl is sodium chloride, but it is dissolved in water. And so we would say that is a solution of sodium chloride. Mixtures of gases are always homogeneous solutions. Always, always, always. And so you can think of the air that we breathe. The air that we breathe is, and I think I mentioned this maybe in a previous lecture, but some rough numbers on that is roughly around 79% N2 or so, and then around 20% O2. And then the rest, that rest of that 1% are things like CO2, argon. What are some other things in there? I think of any of the others. Water vapor, certainly. But so we have this mixture of gases. And so we can absolutely think of the air that we breathe as being a solution of these gases. And it's definitely, and certainly a homogeneous solution because it's all evenly distributed. If we look at some just different types of solutions, liquid solute / solvent solutions are fairly common. And so where both your solute and your solvent are liquids. We can have gas solutes in an aqueous solution. That's what a carbonated beverage is. Pop open your soda, and you hear that fizz coming out. Some of that fizz coming out is carbon dioxide, which is dissolved into the water. And so that's absolutely a solution in which gas is our solute and the water is our solvent. We can also have solid solute solvent mixtures. And so things such as metal alloys, bronze, for instance. Bronze, and we can see the example down here. Bronze is mostly copper, but with a little bit of tin mixed in and sometimes a little bit of phosphorus in there. And so that's what forms bronze. Silver, a silver solid with a little bit of liquid mercury mixed in. That's amalgam, which is used in dentistry. Liquid solvents, we have some ethanol with some I2, it's a tincture of iodine. Some water with some ethanol, there's an alcoholic beverage, which I'm sure none of you know anything about. Liquid solvent water with CO2 gas as our solute. Like I said, that's carbonated beverages. And then we have some other examples here, some gas solvents. N2 and naphthalene, that's what you smell when you are near a mothball. A little bit of N2, because that's the primary component of air, with some water droplets in there. Mist. N2 with O2. There's the air that we're breathing, like we talked about a second ago. A couple things to note is that the solubility of a solute in a solvent depends largely on the polarity of the solute in the solvent. This is one of the reasons that we looked at polarity a couple lectures ago, because the general rule is that a polar solute will dissolve in a polar solvent. Non-polar solutes dissolve in non-polar solvents. This leads us to the term like dissolves like. Polar things dissolve in other polar things. Non-polar things dissolve in other non-polar things. There are a couple other factors that are at play, but for our purposes, that's pretty much the rule that we're going to stick with. We have something called the hydrophobic effect, which describes the tendency for non-polar molecules to cluster together to avoid polar molecules. Compounds that have a polar end and a non-polar sort of act as both, sort of act as intermediates. And so that's something like acetone, for instance. And so the chemical or the Lewis structure of acetone, I'm not going to write the hydrogens out, but there's a CH3 on one end. And we have a C here in the middle. Actually, I'm going to just pull this down a little bit. Restart over, Professor Staples. Here's a C in the middle connected to a C with 3 H's onto it. And it's got that on both sides. But then that middle C is double bonded to an oxygen. And so here we have a definite polar end of the molecule here. And so this is absolutely polar. And the whole molecule would be considered polar based on our polarity rules and our Vesper charts that we looked at before. But we also have, oops, change colors. Here we go. We also have this non-polar end. So we have a side of acetone that is polar and a side of it that's non-polar. So acetone actually dissolves fairly well in both polar and non-polar substances. That's what makes it such a great solvent. When you really need to clean something, get out the acetone. That's going to help because it's got both a polar and a non-polar end, so lots of things will stick to it. When we have an ionic solution, this is another key thing to note. So when I gave that example of our NaCl solution, so here's what sodium chloride would look like as a solvent. There's our ionic lattice that we've talked about. When it dissolves, what happens is that now the chlorine and the sodium ions actually separate from each other and water molecules surround those. So what's known as solvation. And the water molecules will do so orienting themselves to according to their polarities. So Cl with its negative charge, the positive ends of the water molecule, the hydrogens, all orient themselves facing that negatively charged chloride ion. Here's our positively charged sodium cation. And so we see the oxygen of the water molecules all orienting themselves around that sodium ion. That's known as ion dipole interactions. And that's the very reason that ionic substances are able to dissolve in water the way that they do, because the water is able to surround those ions according to their various polarities. And so soluble ionic compounds dissolve because of these ion dipole forces are stronger than the ionic bonds holding the compound together. Not all ionic compounds are soluble, and that's something that's important to note as well. Sometimes for some, those ionic bonds are stronger, and so the compound won't want to break apart. For compounds that are soluble, there is a limit to the amount of solute that will actually dissolve. If we have an unsaturated solution, that can actually hold more solute. We can still dissolve more into it. Saturated solution can't hold any more. And so again, this summer, when you're maybe mixing up your lemonade, the more and more and more and more you add, eventually you're going to get that sludge at the bottom because you've reached the limit of how much can actually dissolve into the water. You've now made a saturated solution. I'm sure you've heard the term electrolytes. Electrolytes are nothing more than ions in an aqueous solution. It sounds fancy, and companies love to market things that way. Oh, our Gatorade, our Pedialyte has so many electrolytes. That sounds sounds fancy and sciencey. That's got to be great for you. They're just ions. That's all it means, is that you have ions in that aqueous solution. Solutions that do contain electrolytes can conduct electricity. In our bodies, this electrolyte balance is regulated by hormones, but it is important to replenish electrolytes. And so if you really legitimately are doing something that is very strenuous and lots of sweat and you're losing electrolytes, replenishing those is very, very important. Incidentally, if you didn't know this already, Gatorade, probably really the first electrolyte replenishment drink, got its name because scientists and doctors for the Florida Gators were trying to find something to help replenish electrolytes for their athletes. They came up with Gatorade. But when a covalent compound dissolves, on the other hand, the covalent bonds remain intact. And the intermolecular forces are then disrupted as we get new solute-solvent intermolecular forces forming. And so don't worry too much about that, but the big thing to know here is that since covalent compounds stay together, we don't form ions. So covalent compounds, when they're dissolved, are non-electrolytes. So that could be something that's important to know. Remembering as well that non-polar solutes dissolve in non-polar solvents. These molecules interact through dispersion forces typically. And so that's what's going to allow non-polar solutes and solvent interactions. Hydrocarbons that have 5 or more carbon atoms are very common non-polar solvents. Things like hexane, very, very, very common non-polar solvent. Dry cleaning solvents, by the way, are non-polar solvents. Most common, tetrachloroethylene. So it's not that no liquid is used, and that's where people think the term comes from sometimes. It's just that the liquid that's used isn't water. And so it's this compound instead, this tetrachloroethylene. And so that's where that term comes from. And so that is all for our discussion of solutions. In the next video, we're going to start looking at the concentration and how we determine how much solute is dissolved in there. And I've been practicing or looking at some new sign-offs. And so as far as solutions go, that's the way the cookie crumbles, USM.